Thanks, Russ. Additionally, 3C-REN is staff, or well, me, 3C-REN meeting. We will we have this picture, this background behind us. So please chat with us if you have any anything you need or any questions. Next slide, please. So quickly, I'll just say, what is 3C-REN? 3C-REN, or the Tri-County Regional Energy Network, is a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties. Programs in our region by offering customized programs that fit all of our needs. 3C-REN offers free services for professionals and households. So for building professionals, 3C-REN has the industry trainings, technical and soft skills trainings, and energy code compliance support. And then for households, we offer free and discounted home upgrades to reduce energy use at home. Next slide, please. So we're funded by ratepayer dollars that we all pay into on our utility bills on a monthly basis. We're trying to bring services that return these ratepayer dollars to our local region that would otherwise not be brought back. Our programs are an investment in our community, which has historically missed out on some of these ratepayer funds. So a lot of the investor-owned utility programs that are out there often don't make it to our territory. Next slide, please. So with that, 3C-REN likes to take a holistic approach to improving energy efficiency in our region, and we engage public sector staff from our local building departments, like our building inspectors and plans examiners, as well as our private sector businesses like architects and contractors. We also work with the broader community members on how energy and buildings intersect in our everyday lives. And these comprehensive services help us reduce energy use in our community and build capacity within the building industry. Next slide, please. So with that, thank you for being with us. I'll talk to you when the course is over, as well as provide a quick survey. But I'm going to hand it over to the person you really want to hear from, which is Russ King. Russ.
Awesome. Thanks, Jordan. Appreciate it. Hi, everyone. Welcome. Good morning. I personally have not quite got used to the daylight savings time yet, so it's still 6:30 by my clock, 6:34. That's okay. It's just I just had to drink a little bit extra coffee. All right, so welcome. Today's class is called Quality Insulation Installation, and we teach a lot of these QII classes, by the way. I have probably 4 or 5 different versions of this class. This particular class is one that we present at CalCerts. CalCerts is a HERS provider. HERS raters are the third-party special inspectors who help enforce the energy code, and QII has been one of the most challenging energy features to inspect by HERS raters, and so we have a lot of classes. And with the new code, it's more important than it used to be with the 2016 energy code. With the 2019 energy code, it's a prescriptive measure. We'll talk a little bit about that. Anyways, again, my name is Russ King. I work for CalCerts. Most of my career is doing residential HVAC design. I'm not quite sure how I became the insulation expert at CalCerts, but it just kind of folded into that. You know, if you don't install insulation correctly, the load calcs are wrong on your house, and your HVAC system could be sized poorly. And so that's the connection there, obviously. So anyways, with that, let's dive into it. These slides, I guess, Jordan, will be made available to everybody at some point as a PDF file. And we're going to reference a document in here. It's called the CalCerts QII Handbook. That is available for free as a PDF download. And I'll tell you how to find that in just a few minutes. So it's new for 2019. So the 2019 Energy Code's actually been in effect for a little over a year now. It took effect on January 1st of 2020. The big difference was prior to this, it was like extra credit. You could voluntarily choose to say, hey, I need some extra credit to make my house meet the energy code, so I'm going to do this QII thing. Well, in the 2019 code, And it goes by permit date. So anything permitted on or after January 1st of 2020 falls under the 2019 code. They made it what's called, and unless you're into the energy codes, you probably don't know what that means, but a prescriptive requirement basically means it's a feature that's on the house you're being compared to. All right. So when you demonstrate compliance to a house for the energy code, you're being compared to a what we call a standard house. And a standard house has all these features on it. And you can build your house however you want to, as long as it uses the same amount of energy or less than the standard house. So this feature, this QII feature, is on that standard house. So if you choose not to do it, now your house is being compared to a house that has it, and that just puts you in a big hole. Now you have to do other things to the house to bring it up. And as it turns out, it's pretty difficult to make a house meet the energy code for 2019. So any holes that you dig are going to be big holes. And so the bottom line is, in the 2019 code, it's rather difficult to get a house to comply without QII. So what that means, it's going to be on a lot more houses than what it was before. That's really the bottom line. Okay. So quality installation is quite a mouthful, so we call it QII. It's a procedure for ensuring that installation has been properly installed and that air sealing has been properly performed on a home. Okay, so there's a couple important things in that statement there. QII is not it's not installing the insulation correctly. It's a procedure for ensuring that it was installed correctly. So QII is actually an inspection procedure. And so what this means is someone is going to come out and inspect the house and look for certain things. From the installer's perspective, it would be nice to have the answers to that test, wouldn't it? If someone's going to come out and do inspections and look for stuff and check things off, it'd be nice if you had the answers of what they were looking for before you start installing. So that's kind of the purpose of this class. So a lot of people will say, you know, where did they come up with this stuff, this QII? I've never seen this stuff before. Why are they asking me to do this? Why are they telling me to put sheetrock on the attic side of an e-wall? And, you know, the Energy Commission didn't make this stuff up. It comes from industry standard practices that have been around for a long time. In fact, one of our training handouts is a tech bulletin. I want to say it's from 1997. From NAMA, the National Association of Insulation Manufacturers. That's where all this stuff comes from. QII is what the manufacturers of the insulation say, this is how you should install the insulation. If you want our insulation to work the way it's labeled, the way we claim it works, you have to install it this way, okay? And so another good, as I mentioned, a good reference is this CalCerts QII handbook. It's available for a free download. Just Google this, CalCerts QII handbook, and it'll come up as a link, and you click on it and it'll download the PDF for that. This is a handbook that I wrote a long time ago when QII first came out. The actual protocols for QII is called the Reference Appendix Section 3.5, and that's put out by the Energy Commission, and it's 3 diagrams and all these pages and pages of text. And so we basically took that, we kind of reformatted it, and we added a whole bunch of diagrams and photos and made it a much more useful user's guide. It's intended for HERS raters, for installers, for builders, for architects. So it has a lot of really good information. All the diagrams you see in this slide presentation are from that QII handbook, okay? So as I mentioned, the official protocols for doing QII is the Residential Appendix Section, the protocols. That's the step-by-step instructions that a HERS rater has to follow in order to do the QII process, okay? Now, the installer can follow those same things in order to pass QII, but do be aware that the QII itself is an inspection and verification process. Okay, the actual how to install stuff, that comes from the manufacturers, and the QII is based on all those manufacturers' instructions. Okay, for newly constructed building, the QII procedures apply to the entire thermal envelope, the entire thing. You can apply QII to an addition, and then QII only applies to the new walls that are created. But for a newly constructed house, it's everything: walls, floors, ceilings, windows, doors, everything on the thermal envelope. Okay. So QII verifications have the highest failure rate of any HERS verification. When QII first came out, it was probably failing 90% of the time. QII was a fail. When a HERS rater goes out to do an inspection, 90% of the time, it failed on the first inspection. Then the HERS rater had to point out all the problems, and then to the development of the QII handbook is because it was just failing so often, and raters needed something to give to installers to say, here, follow this, okay? The other important thing that gets mentioned later on, though, is that there are some forms that have to be filled out by both the installer and the HERS rater. They're very similar. They're called the ENV 2021 and ENV 22. And one version's filled out by the installer, and it's basically saying, yes, I did this, yes, I did this, yes, I did this. And you fill all that stuff out. The HERS rater confirms and does their verification and says, yes, they did this, yes, they did this, yes, they did this. And so it's just a checklist. That form, the ENV 21 and the ENV 22, one happens before the insulation goes in to check the air barriers. One happens after the insulation goes in to check the insulation itself. Those are another good sort of answers to the test, if you will. That's a good thing it's really a good idea to use that checklist as you're sealing the house, as you're installing the insulation. And then at the end, you fill it out and say, yes, I did everything I was supposed to do. Then the HERS rater comes in, checks everything, says, yes, they did everything they were supposed to do. That's ideal. That's how it should work. Okay. Everyone needs to know exactly what is expected before the HERS rater does their inspections. Okay, so that's use the QII handbook, use the forms as a checklist. If there's any strange situations that we, for some reason, haven't drawn a diagram for, or it's just a weird kind of odd situation that you've not seen before, ask us, let us know, talk to the HERS rater, say, hey, what are we supposed to do here? And we'll come up with some sort of thing that works. Okay, it's pretty straightforward when you boil it down to its very essence. Air is passing through it. So in order for insulation to work, you must first have an airtight shell. All right. And then on vertical walls, what happens is if you don't have something to stop air movement on both sides of a vertical wall, what happens is you get these little thermal siphons through. And I've got some diagrams of this. But if you boil it down to those very simple concepts, you must have an airtight shell first. The insulation must be installed well, and then vertical insulation, such as walls, has to have an air barrier on both sides. If you just follow those basic steps, you might run into. The most difficult part of QII is probably the logistics. And by logistics, I mean, you've got a very small window for an inspection to happen. I've been out on subdivisions where the insulator is putting insulation in and the sheetrocker is literally standing there waiting for the insulator to finish, and they start covering it up with insulation. Well, the HERS rater has to see that insulation before the sheetrock goes on. Okay, that's very important. If the insulation gets covered up before the HERS rater sees it, that's an automatic fail. Getting early on when QII first started is HERS rater would call me up and say, hey, I'm out here to do this inspection and they've sheetrocked over the insulation. What do I do? I said, you have no choice. You have to fail it. That's a fail. If you can't verify that they did it right, that's an automatic fail. And so at that point, their choice is to either tear the sheetrock off so the HERS rater can see it, which they have yet to ever do. They just don't do that. Or you go back to the energy consultant and say, hey, we can't do QII. Can you rerun the house without this QII credit and see what well, in the 2016 code, that wasn't hard to do. You could, put in a more efficient water heater, maybe blow some extra insulation in the ceiling or something like that and get it to pass. But in the 2019 code, it's way harder. It's much harder. One of the things I've heard people do is if they made their house pass with QII and then had to take QII off and get it to pass again, one of the things that they can do is put in a whole house battery, like a Tesla battery. That's a very expensive thing to do, okay? So it's not an easy thing to fix after the fact, which is why we're trying to get, let you guys know. So there's no excuse to say, well, I didn't know what QII was, or I didn't know how to do it, or I didn't know I couldn't cover up with sheetrock, all right? So be very, very mindful of that. Okay, this diagram, I put this together just to show how complex the QAI process can be. So let's say there's a subdivision and they have all these different steps along the way, and different builders use different terminologies, but let's say there's a pre-design stage, and then there's the actual design, and then there's a design review. Then they go into grading, framing, the rough in stage, insulation stage, drywall, finish, and then final inspection. Okay, so those just examples of the different stages of construction. And I suppose this could apply to a custom house as well, but this is fairly typical for subdivisions. All right, so so those are the columns, and then the rows are different responsibilities. These are different people. All right, so you've got your energy consultant, they're the one code. You've got the builder and the architect who are sort of responsible for making sure the building gets built correctly. Then you've got the HERS rater, who's that special inspector. You've got the insulation installer. You've got the framer, the drywall installer, and then a whole bunch of miscellaneous trades. The electrician comes into play, the window installer comes into play, the HVAC contractor comes into play, and those all have to do with the air barrier, right? You know, the penetrations in the air barrier that have to be sealed and stuff like that. All right, so, and then every box that you see words in is where something has to happen, is where somebody has to do something in order for QAI to happen smoothly. If you don't do some of this early stuff, what happens is you get towards the end and someone's like, oh, I didn't know who was supposed to do that. I didn't know who was supposed to seal around this. And then there's a bunch of finger pointing and then it just gets becomes a big mess of QAI is very important. And so this diagram is in our the QAI handbook. So, and it's a good example. But I would say if you know the project is going to have QAI, is contact your rater, your HERS rater, as early as possible and get them involved in the process, and they can help you sort of plan this stuff. They can even kind of like review the plans, and say, oh, look, you've got this shower on an exterior wall. You got to be careful of that. Or, oh, you've got these skylight wells. You have to be careful of those. You have to be able to sheetrock the attic side of a skylight well and things like that. Okay, so get your rate. All right, so some important definitions. The first one is continuous air barrier. So this is a combination of interconnected materials and assemblies joined and sealed together to provide a continuous air barrier to leakage through the building envelope. So the best way to describe this is if you were to pressurize a house with a giant fan and pressurize it like a balloon, where is that air going to go? How is that air going to escape? And if you have a continuous air barrier, it shouldn't escape. I mean, there's always going to be some little holes. Like every window has a weep hole in it. So when moisture comes down, gets into the track, there's little holes so that moisture can go to the outside of the building. Those are always going to be there. So you're always going to have a certain amount of leakage in a house. But any place where insulation is going to be touching, you don't want there to be any leakage. Because like I said, as soon as air is passing through the insulation loses all its R value. Okay, so continuous air barrier. So you really have to look at a set of plans and where all the different surfaces join together. A really complicated one is when you have a two-story house and you've got bedrooms over a garage, an unconditioned garage. That ceiling of when those floor joists come along and meet the house on the first floor, those have to all be sealed, and it's very common to leave those open. Then air can pass from the house, get out over into the unconditioned garage, and then heat conducts through the sheetrock ceiling into the garage. So you just have to draw a line and define the air barrier very carefully. Okay. Compression is just insulation. Fiberglass bats are rated for a certain R value, and that R value only applies when they're fully lofted. So for example, an R13 bat is only R13 when it's 3.5 inches thick. If you squish it down, which is by the thickness, okay? If you reduce by half, the R value goes by half, okay? And so compression is allowed to a certain point as long as you're accounting for that reduction in R value. But after a certain point, it becomes too much, all right? And 30% is the break point. After a 30% compression, all the fibers in the fiberglass are really, really close together, and the R value starts dropping more steeply. in relation to thickness. And so they basically say compression by more than 30% is not allowed. All right. And this kind of shows you how if you take an R13 bat and you compress it a little bit, it's really R11. If you compress it a lot, it's we don't know. It's just too much. And R21 is R21 at 5.5 inches. So in a 2x6, if you compress it a little bit, it's really R19. If you compress it more, it's R12. And more than 30% is not allowed. Okay. But if you do compress it a little bit like this, you have to realize that it's no longer R21, it's an R19. And that's what you have to, if you're required to have R21 in that wall, it won't pass because you're only getting R19. But if they modeled R19 and that's all that's required, it's okay to compress an R21 a little bit, as long as it doesn't go below what's required as the R value, okay? Draft stops, this is where we kind of, QAI starts overlapping with smoke fire code requirements, okay? So any place that you have a penetration passing through or passing through floors, okay, you have to put we always call them fire blocks, but they also call them draft stops, and that's to prevent air movement, both for fire safety issues as well as energy, okay? And so here's a situation: you got a 2-story house, you've got some ducts coming down from the attic passing through the house, and you see these little holes here. Those have to be sealed up. First of all, this piece of OSB that's here, that's the actual draft stop. The other requirement is that it has to be sealed against air movement. So these holes are going to have to be filled with something. Sometimes you'll see them use sheet metal collars. Sometimes you'll see them cut sheetrock that tightly fit around the ducts and things like that. Just to prevent air from passing through here. The other one is, if it's blown-in ceiling insulation, is to keep the insulation from falling down inside this chase, okay? All right, gaps, edges around insulation where the insulation is not in contact with all 6 sides. We'll talk about 6-sided contact in a second. So gaps occur when the insulation length is too short for the cavity. And so gaps in insulation is avoidable and just not allowed. Just don't do them. So here's some examples. So they just didn't tuck it in the corner here very good. They didn't trim around this junction box, so you get these gaps like that where air can move through, where there's no insulation essentially, okay? So those are an automatic fail. Hard covers. Ideally, if you walk up into an attic before they put the insulation in, what you'd really like to see is this nice flat, smooth attic all the way across, their ceiling, I should say, flat, smooth ceiling all the way across. But architects like to drop ceilings for different, architectural interests, the house and things like that. And sometimes, if you have 10-foot ceilings and a bathroom is really narrow, they like to drop it down so it doesn't feel like you're standing in a tube, stuff like that. So you have a choice. If it's a fairly narrow opening, you just put a hard cover across it like this. So this is just a piece of sheetrock. Jordan, can you see my mouse, my pointer, the screen? Okay, good. So you see this piece of sheetrock on here. And what that is doing is preventing the insulation from falling down into the ceiling. So you have inside the house, you've got a tall ceiling and a shorter ceiling and another tall ceiling here. So the easy way to insulate this is to put a hard cover there. But it depends on the width of this room, 2 or 3 feet. If it's a closet or something, it's easy to put a hard cover. But if it's really wide, it's harder to do. And so what you have to do then is these walls then become insulated walls. So this is too wide to put a hard cover across the top here. So what you have to do is now your air barrier, instead of going across the ceiling like this, your defined air barrier, your boundary, your thermal boundary, now follows this dip, this drop like this. And so this becomes ceiling, this is insulated wall. And so now you have to put a dam here to keep this insulation from falling over. You have to put an air barrier on both sides of this vertical surface. And then this ceiling insulation down here has to be proper depth and R value. So it gets a little complicated when you start doing it like this. But before the QAI protocols came out, what would happen is they would just blow insulation. It would fall down inside here. There'd be a little part of uninsulated wall up here. This insulation would just sort of taper down and fall into this hole, and you're not getting anywhere near the R value. If you were to look at that with an infrared camera, you would see all that. And so that's why you have to do this for QII. Okay? Another kind of unusual term that insulation contractors aren't used to seeing, but it's called net-free vent area. And that's basically the actual opening of a vent for a vented attic is required by code to have vents in it. And they put all these vents either in the soffits or whatever. You could have the O'Hagan vents in the roof and stuff like that. The net-free vent area is the actual open area that air can pass through after you subtract out the wires and the louvers and all this other stuff, okay? Now, the reason that's important is because when we start baffling these vents in the attic, this net-free vent area of whatever that vent is has to be maintained all the way up. Baffle to be pushed up against this insulation because then you're blocking the vents. These vents are sized for a reason, and we don't want to impede that. I've been in houses, you know, a long time ago before QII, where they wouldn't even baffle. You would walk around the outside, you'd look up inside these vents, and the insulation is blown right up to the back side of the screen. Okay, and now they have no venting in the attic, and the attics get super hot. Okay, and that was why I was called out. It was a comfort complaint. All right, so whenever you baffle these, make sure that vent area is maintained. You're also going to start seeing a lot of unvented attics. That's a whole different situation, and we'll talk about that in just a minute. But this is a vented attic, a typical vented attic. The importance of attic ventilation and baffling. This is an unbaffled attic vent here. Here's a soffit vent in a windy situation. Look what happened. The wind actually blew all the insulation away from this baffle here. I've also seen pictures where there's an O'Hagan vent in the roof, and directly below the O'Hagan vent, about 3 feet down, was a big circle of no insulation. And it was almost like a little tornado occurred directly below this O'Hagan vent and made a circle in the blown-in insulation. Now, the O'Hagan vent was like 3 feet above, but this was somewhere down in Southern California where they get the really, really strong winds, okay? So baffling is very important. It allows the air to come over. It prevents the wind from blowing the insulation away and stuff like that. Okay? All right, voids and air spaces. So a void, so we talk about gaps. Gaps are typically around the edges. Voids are where the insulation doesn't completely fill the space that it's supposed to fill. And so if you look really carefully at this photo, you'll see there's a stud bay here, and you see this straight edge laid across the studs. And if you look at the shadow of the straight edge, you'll see that it dips down like this. And so what that means is when the sheetrock gets put over the top of this insulation, where the shadow line is, that little bit of light that you see there is going to be a void. That's what we call a void. So, and then what happens is behind that sheetrock, air can circulate around, and it's not like it's this little, you know, wind machine happening back there. It's a very slow migration of air, but what it does is it reduces the R value. It reduces the R value of the insulation by a substantial portion. Okay, and it's enough to say, look, we just don't want this to happen, so don't do it. Right. And here's kind of just a diagram. So on the warm side of the house, what happens is the air will rise actually inside the insulation. The air will rise up. And if you give it a path to fall back down by having a gap on the other side, the air falls down and then it rises up, and you get this thermal siphon happening inside the wall. Okay. If the sheetrock's not there, it's even worse. Okay. Which is why you're supposed to put sheetrock on both sides of a knee wall in a house, is to stop this from happening. In not too long ago, before QII, you go up in an attic and you look at the backside of knee wall and you see the insulation. There might be a strap across it, and a knee wall is the wall that separates the house from the attic. So anytime you have a vaulted ceiling, you typically have a knee wall. So if you were to go up in the attic and look at the backside of a knee wall, typically what you'd see the backside of the insulation. And if you drill through it, you go through the insulation, through the sheetrock into the house, okay? Well, now with QII, you have to have sheetrock or an air barrier of some sort on both sides of that wall. So you shouldn't be able to see that insulation anymore. And this is why, is because you get these thermal siphons through. All you have to do is put an air barrier in contact with this insulation, and it stops those thermal siphons, okay? Because there's no place for the air to drop on one side. And so it doesn't stop it 100%, but it stops it so it's negligible, okay? So again, I mentioned the importance of defining the thermal boundary. So look at this little section of this example house here. It's a 2-story house. It's got an attached garage with some attic up above it. And there's a vented attic up on the top here. We've got some floor joists. So there's sort of this interstitial space, I guess you'd say, between the floors. And then this house has a raised floor, okay, with a vented, unconditioned crawl space down here, right? And then also notice there's this fiberglass shower insert here, and it's pushed up against an exterior wall, right? So let's look at that. So the first thing to do is define your air barrier. So the air barrier actually has 2 sides to it. There's an inner side and an outer side, okay? And let's see, the air barrier has to be insulated, continuous insulation all the way around. So when you follow this air barrier, there needs to be insulation, an airtight air barrier that stops leakage. And so when you start getting to where this vertical wall meets the ceiling and stuff like that, you have to make sure that that's all sealed and blocked off so that air can't escape. Notice that the between floor space here is inside the air barrier. So that's considered conditioned space. Between floors is considered conditioned space. So you don't have to worry too much about caulking and sealing between these. There are smoke fire requirements that you do, but it's not as important. You don't have to insulate in here and things like that, okay? So notice where this shower insert is pressed up against the wall. There has to be an air barrier behind it. That's important. That gets missed a lot. So they actually have to put a piece of sheetrock on the wall before this tub or shower or any kind of fiberglass or one of these inserts that slides up against the wall, because this is a vertical surface, and so it needs an air barrier on both sides. This shower does not count as the air barrier. It does not do a good job. Okay. And then sealing around bottom plates and floors, that's important. Okay, there's a lot of different ways to do it. You can use this foam that they roll out and put the bottom plate on, or you can caulk and seal it, all right? The important thing is that it has to be inspectable. The HERS rater has to see that, yes, you did something. We've had people just run a bead of caulk down the middle, and then when they stand the wall up on top of it, you can't see it. So there's no way to know that it's actually there. So if you caulk and seal it, make sure the caulk is visible. If you put these foam gaskets on there, those are pretty easy to see because they're the same width as the bottom plate typically. Okay. So here's just kind of a section view. There's 2 places pressurizing the house with a big fan. So this house over here is under high pressure and air wants to get out. Well, around the bottom plate, there's 2 paths the air can take. It can either go over the top of the bottom plate, or it can go between the bottom plate and the slab. Both of those places have to be sealed. Okay, so this is the gasket. This can be caulking and sealing, but they're also going to have to run a bead of caulk along this bottom plate here to prevent air from going on either side of it. All right. If it's a raised floor, very similar situation. There's 2 paths the air can take, go between the subfloor and the bottom plate, or it can go over the bottom plate and between the exterior siding. Notice that you don't have to seal down here because this is not part of the conditioned space. Okay, you don't have to seal here. You don't have to seal here or seal here because this is not pressurized. This up here is pressurized, all right? And we've defined the air barrier as the subfloor and then going up the wall. Now there are construction practices where the crawl space is conditioned. That's a whole different beast. So in that case, the insulation would come all the way down this wall to here, and there would not be insulation across the floor. And that's a different air barrier definition. Okay, so that's a different beast. Any penetrations through the bottom plates have to be caulked and sealed, even if they're between floors. This is kind of where the smoke fire code overlaps with the QII. You might say, well, this is a between floor space. Why do I have to caulk and seal that? Well, it's not so much for energy. It's more of a smoke and fire thing. We have a 2-story house, and we're talking about between the 1st and 2nd floors. But you do have, if it's going down to a crawl space, you also have to do it, and you also have to have. Here's looking down on a what do we call that, a draft stop. Notice how they caulked around here like that. You see that caulk? That's a good sign. That's what you want to see. So again, if this house is pressurized, air is trying to escape around these ducts and go down into the crawl space. that's what you want to stop, okay? Now the ceiling of a conditioned space, and this is between conditioned and unconditioned space. This does not apply to the first floor of a 2-story house. This applies to the first floor of a 1-story house and the second floor of a 2-story house. So you have unconditioned attic above it and conditioned space below. All these different little spots need to be sealed, need to be caulked and sealed. Again, this house is pressurized and air wants to escape through all of these things. And we break this down, we look at these individually in the QII handbook. So just be aware, any place that air can escape and get up into the attic needs to be sealed. Any penetrations in the top plate have to be sealed, whether it's for copper water piping, whether it's for waste vents, whether it's for wiring, whether it's a knot hole, it doesn't matter. All of those have to be sealed somehow, okay? Any penetrations in the sheetrock between conditioned and unconditioned space, so we have attic above, these have to be sealed. Now, again, the question is, as I mentioned earlier, whose job is this? Is it the insulation contractor? Is it the electrician? Is it the HVAC contractor to seal around the register boots? Whose job is it? That all needs to be defined as early as possible in the contracts, okay? Because what happens is the HERS rater gets out here and goes, oh, no one caulked and sealed around your electrical boxes, and the insulation contractors go, oh, that was the electrician's job, and the electricians say, oh no, that's the insulation contractor's job. Whose job is it? That needs to be defined, or you just get people pointing fingers at each other. One thing about fire sprinklers is always follow the manufacturer's instructions. Some fire sprinklers allow you to seal around the sprinkler. It cannot seal around the sprinkler. If you want to make it airtight, you have to build a little box up in the attic. So again, whose job is it to do that? And then some manufacturers say, no, you can't even do that. So a HERS rater is going to come out and say, how did you seal around these fire sprinklers? And if you say, oh, the manufacturer says we don't have to, the HERS rater is going to say, well, let me see those instructions. Let me see those specs to confirm that, okay? So always follow the manufacturer's instructions. Can lights, any penetration in the ceiling has to be sealed, but because air can actually pass through the can light itself. And these have actually been around for a long time. IC and airtight rated can lights are required. That's something the HERS rater is going to check for. And all that means, IC means that it's insulation contact. So the insulation can actually touch this box, this sheet metal box up in the attic, and it's safe, all right? And then airtight means that the light can itself has been manufactured in such a way to reduce leakage through it, okay? The old ones, you go into some of these older houses and you look up, you can actually see daylight through the can lights up into the attic. Those allow a huge amount of leakage. All right, so wall cavities, as I mentioned, again, if you pressurize the house here, where is that air going to escape? Air will get behind the sheetrock, the inside sheetrock, and through outlet covers and stuff like that. So the house is pressurized, that pressure is going to get inside the wall, and now the air is going to want to escape between the top plates and the exterior siding. It might want to escape between the top plates if you have a double plate situation, and it's going to want to escape between the sheetrock and the top plate and go up this way. So there's actually 3 places that need to be sealed when you have double top plates, okay? Some of the ways you can seal sheetrock, the top of the sheetrock to the wall is different kinds of foam gaskets. You staple those up first. The sheetrock goes over the top of it. This is kind of a pain in the butt. A lot of sheetrockers, the technique I've seen is they lean the sheetrock up there and then they slide it up into place and then screw it into place. And what happens is when they slide it up, it tears this little gasket off. So they've had to change the way they do it. Instead of sliding it up, they have to lean it up against this stuff and then screw it in place, okay? So these can create a bit of extra work. It doesn't have to be these foam gaskets. They also make a spray-on foam that goes on soft and it stays soft. And so when you put the insulation or the sheetrock on there, it makes it sealed. So there's a lot of different ways to do that, but it is something that the HERS rater is going to look for. You can also, after the sheetrock goes on, you can actually go up into the attic and just run a bead of caulk or foam along these seams right here, okay, because that's where air is going to escape. And this is not just exterior walls, this is interior walls as well, okay, because this is a potential place for air to get inside that interior wall, come up and come between the top plate and the sheetrock and escape up into the attic, okay. Windows and doors, that's usually the windows installer's responsibility, not always, but usually, because they typically have a special foam that they use around windows. It's a whoever's job it is, it needs to get done. Okay, so windows and doors and any kind of penetrations through the wall need to be caulked and sealed. All right, let's talk about spray-on polyurethane foam, SPF. So that's becoming more and more popular, and that's that spray-on foam, and it expands out, and they scree it off to be the depth of the studs. Okay, the nice thing about it is that it's an air barrier and it's an insulator. So there's not two steps where you have to caulk and seal and then insulate. This, when you apply the insulation, it does the sealing for you. Okay. And it is okay as long as it meets the R value, the required R value, whatever's specified on the CF1R. If it says this has to be R19, you need to get R19. It is okay to have voids between the sheetrock and the insulation as long as it meets the R value, okay? And there's also going to be some specifications depending on the type of SPF that you have to have a certain thickness in order for it to qualify as an air barrier. So for closed cell polyurethane foam, 2 inches. For open cell, it's 5.5 inches of depth. And what that is, so air is going to want to leak out through this corner here. So if you had a void coming up through here, you wouldn't get your 2 inches, so you wouldn't get your air sealing. It's okay to have a void in the middle as long as you get your R value. Okay, the HRSrater is going to walk around with a little, like a piece of curtain rod, or sorry, coat hanger, a little wire or welding rod or something, and poke it through the insulation and measure the depth. Okay, you are allowed to have voids for SPF because SPF doesn't allow that thermal siphoning like fiberglass bats do. Okay, roofs, walls, and ceilings. Let's see, completely fill the cavity. If you use rigid board insulation, you have to tape the seams. You have to have the right thickness, the right R value. You have to tape the seams and things like that. So there are not just bats, but the QII applies to a lot of other types of insulation as well. And I mentioned earlier, if you have a vertical surface of any kind, whether it's just a regular exterior wall or a knee wall or a skylight well or something like that, you have to have an air barrier on all 6 sides. Okay, so any rectangular box or a cube or like a dice has 6 sides to it, right? 1, 2, 3, 4, 5. Cube or anything like that has 6 sides to it. There's left, right, top, bottom, front, and back. That insulation needs to be in contact with all 6 of those surfaces. Okay, so that's what we'll call it, 6-sided contact. And then a lot of times in these wall cavities, you have various kinds of obstructions. You can have piping, you can have outlet boxes, you can have wire, all kinds of stuff can cause it to be difficult to insulate. And so what you have to do is you have to cut around that stuff. You can't just cram the insulation in over a stud bay that's got a pipe running through it, because that pipe's going to hold the insulation out, and then you're going to have a void, which is going to promote the little thermal siphons. Okay. So you have to either cut it, the insulation, and kind of place it in there carefully. You have to trim it to get it to tuck in behind it, or we do what's called delaminating. If you've ever looked at fiberglass bats, they're in layers, and you can split those layers, and it's called delaminating. And you can put half the bat behind the wire, half in front, and tuck it in all nicely. That is something that the HRSraters will look for. Okay. You don't see a whole lot of this, but I've seen a few of them, and it's kind of cool to watch them do this. They'll put this in cover, they'll staple it. It's a fabric. They staple it over the stud base, and then they poke these holes, and they take this hose and they fill it with this loose fill insulation. It's fun to watch. It fills up, and the nice thing about it is it gets behind all the wires, it gets behind the plumbing, it gets behind the junction boxes, and does a nice job. But they have to put in enough so that it has the right density. And so we do a little sample called a cookie cutter test to make sure that it's the right density. You can usually tell by feeling it. But if you see any, like if they did some open spots along the top here, you might see some open spots around junction boxes and stuff like that. So they typically overfill these has been my experience on these. But anyways, it's just another type of insulation that has to be done correctly. As I mentioned on the rigid foam insulation, it's very popular, very common to put rigid foam on the outside of the house for a one coat stucco system or something like that. And then they put the siding over the top of it. If you do that, that makes a great air barrier as long as those seams are taped. So you notice that all the seams in this rigid insulation is taped to prevent air from passing between those pieces of rigid foam insulation. Okay. Narrow frame cavities, you know, it'd be nice, your house has got 16-inch on center studs. It would be nice if every single stud bay was 14 inches wide. But it just doesn't happen. So you've got these odd size stud bays like this one here. Basically, the insulation has to be trimmed to fit those spaces. Okay, you can't just take scraps and stuff them in those holes, which is very common. You have to trim it and properly fit it in there so that there's no gaps, no voids, and no compression. Okay, so narrow frame cavities are important. Another one is the typical way to frame an interior wall. So you got an interior wall teeing into an exterior wall. The typical way to do it is to space the studs out like this. And what that does is it gives you a little edge so that you can nail the sheetrock to, okay? Well, what it also does is it creates on the outside is it creates this void, this pink box here. It creates a void that has to be insulated prior to the siding going on. That's at a different time in the schedule than the insulation on the inside. So that's potentially an extra trip for the installer to come out and insulate these voids. And so what a lot of people are promoting, and I certainly promote, is alternative framing techniques that don't create those little channels on the outside. So same thing on corners as well as interior T-walls. So here's those studs. This is the traditional way to do it. This stud gets moved out, so there's this little edge to nail the sheetrock to. It creates this void that has to be insulated, okay? Well, instead of framing it like this, frame it like this, and then you can insulate this whole thing from the inside. Okay, so that's a detail that the architects, that the framer should put on the plans, or the architect should put on the plans for the framer to make sure that this happens. Otherwise, you have to come out early and insulate this void. Okay, we talked about tubs and showers. So this particular wall, there's no sheetrock back here. Hers would fail that. All right, this one is a jacuzzi tub against an exterior wall, and you see this piece of air barrier here. Okay, that would pass, except there's this exterior access panel to get to the jacuzzi motor and everything on the outside of the house. There's a metal door on the outside of the house that they have to open up and reach through to service this jacuzzi tub. That has to be insulated. Okay, but this is the important part here that for this particular example is. Look how they put this air barrier. That's good. That's what they want to see. And this air barrier doesn't have to be sheetrock. It can be, I think this is called thermoply. It's kind of like a thin cardboard material. There's actually fabrics that qualify as an air barrier. There's a whole list of them of what qualifies as an air barrier. Rim joists. Rim joist is the only exception to the rule that a vertical surface has to have all 6 sides. So if you were to follow that 6-sided for vertical surfaces, you would have to put sheetrock on the inside of this rim joist here. Rim joists are the one exception, okay? By the way, the Energy Star program requires that. The Energy Star program requires a piece of air barrier on the inside of this rim joist, all right? But this wall here and this wall here needs an air barrier on both sides, but the rim joist does not. Okay. Jordan, was there a question in the chat? I think I saw something pop up there.
Sorry about that. Yes, so Daniel asked if there's a list of air barriers in the QII handbook.
Yes, there is. Also in RA 3.5, but in the QII handbook as well. It's a list of about, gosh, it's like 20 things. But the top 5 are sheetrock, OSB, rigid foam insulation, There's a product called Thermoply, and then what was the other one? Plywood or something like that. Those are all fine. But then there's a whole bunch of other things on that list. And then there's also I think it's called the PERM rating. It's the permeability rating. It says any material that can be tested to this PERM rating will qualify as an air barrier. So yeah, it's a pretty comprehensive list. So here's some rim joy. So they sprayed up in there. That looks really good. This is fiberglass bats. It doesn't look so good. Some of this compression down here, you see some voids and stuff, probably wouldn't pass. But the point here is this is the rim joist that's being insulated, okay? But this is not as clean as it could be. I mentioned knee walls and skylight shafts, so those are considered a vertical boundary, a vertical surface, so they have to have air barrier on both sides. So again, a knee wall is any vertical surface, any wall that separates the house from attic. All right. So normally you climb up into this attic and you look at the backside and you'd be able to see the insulation. That's not allowed anymore with QII. That would have to have air barrier or something, sheetrock or something on the attic side, as well as the sheetrock on the house side. Okay. This is also a knee wall here. Okay. This is actually where the term knee wall comes from. Is a lot of times in rafter ceilings, they'll build a room inside of a rafter ceiling, and that lower wall that's down at knee level between the house and the attic, that's where the term comes from. But it also applies to these up here as well. Covered porches, knee walls. Okay, so you've got a knee wall, something like this, vaulted ceilings. Okay, you need air barrier on both sides of the ceiling. You also need this little dam up here. You also need this little block right here. So this wall here has to have 6 sides. Okay. Skylight wells, sheetrock on both sides. This one's kind of interesting. Architects like to put these pop-outs. Okay, they just like frame out a wall to kind of give it a little architectural interest, like windows and stuff like this. So if you took a slice horizontally through a wall near a window, you see these boxes framed out on either side of the window. We call those bump outs or pop outs. Now there's a lot of different ways to insulate that, but the key is to define your air barrier. What are you defining your air barrier? The most common way to do it is just straight across this wall here. Okay, the interior wall, that's going to be the air barrier. These exterior pop outs, they're just decorative. But this wall here has to have an air barrier on both sides of it. So they're going to need to put sheetrock or something here inside this pop out. You could alternatively go follow the pop out, but that's a lot more work if you ask me. Okay. The other thing is completely fill it. Completely fill this bump out with insulation. Now this is your interior, this is your exterior. You've got 6-sided contact. That's good to go. All right. The top one's probably the most common way to do it, but you have to put this air barrier here. See my pointer, okay? There's a lot of sheet metal tie downs for structural purposes, especially along the coast, higher seismic regions. You get these big metal strong walls and stuff like that, these big metal tie downs and things like that. Insulate those as best you can. You basically cannot have metal going all the way through the wall because that conducts heat like crazy. And this only applies between conditioned and unconditioned space. If this is out in the garage, don't worry about it because you're not insulating that wall anyways. But if this is interior to the house, or I should say between the house and unconditioned space, you've got to do something about this. Insulate as best you can. You technically don't have to meet the target R value at this particular location, but you can't have metal going all the way through the house to conduct heat. You have to put some sort of a thermal break over that metal. This is my least favorite topic of QII because it gets missed so much, and it's poorly spelled out in the code, okay? And the residential compliance manual that the Energy Commission puts out, that's kind of like the user's guide to the code. Sorry, I'm just checking the time here. We're okay. Actually carried over some old language into the current version that says you can have a full width header. So basically what we have here is a 2x4 wall above a door, okay? And the normal way to do it is to put a full width header above the door. Well, if you go talk to the structural engineer, 90% of the time they'll say, no, it's not required to be full width. We just do it because it's easier to frame. It's easier to frame a if this is a 2x4 wall, a 3.5-inch thick header above the door, when you really only need a 2-inch header to meet the structure requirements, they go ahead and do a full width header because it's just easier to frame. Okay. The problem is QII requires that header be insulated. And so it needs this insulation. So the header needs to be narrow enough to meet the structural requirements, but also to get in R3 on a 2x4 wall and R5 on a 2x6 wall. Okay. Now,
hey, Russ,
the reason you may not see this, yeah.
Sorry, we had one quick question just before you get too far down the rabbit hole here. So Michael Hicks asked, does closed cell spray foam achieve the backside air barrier on a knee wall?
Yes, it does. It does. Yep, absolutely. Good question. Yep. Okay, so what you may not see a lot of these headers, because what happens a lot is they're going to go ahead and put rigid foam on the outside of the house anyways. So the house, will have a one-coat stucco system. So there'll be a rigid foam on the outside that meets the requirement for insulated headers. So if you're putting rigid foam on the outside of the house, you don't have to insulate the header. If you're not putting rigid foam on the outside of the house, you do have to insulate the header. And the requirements actually say it has to be on the interior of the house. I don't care which side it's on personally, as long as it's there. Okay. So do be aware of that. Insulated headers is a big deal, and it gets missed a lot. Okay. And here's what I was saying. You have a full width header. If you have insulation on the outside of the house, you don't have to insulate the header. That counts as the insulation for the header. Roof trusses, if you're going to, well, I got another slide here in just a second, but if you're going to use fiberglass bats in an attic, there's a lot of issues with, and it's very, very difficult to meet QII with fiberglass bats in an attic. If you have plain rafters, if it's an old-fashioned rafter where this is like a 2x10 or a 2x12 holding up the ceiling, what you have to worry about is this gap. So what you want, if these are 24 inches on center, you want a 24-inch wide bat so that it fluffs out and comes in contact with it. If you put in what would that be? A 20-inch wide bat between these things, you're going to get this gap, and that's a fail. So it has to be full width bats, right? The other problem is if it's the most common way to do ceilings is with roof trusses, right? Those engineered roof trusses. And so it's a triangle with all these vertical truss cords going across. Well, those vertical truss cords, what they do is they hold the insulation away from each other. The two bats that go down between them, this gap that follows along that roof truss. And if you look down on it, it looks really tiny from above, but it actually goes all the way down and through and follows along. So that's a gap, and gaps are not allowed. So even though it doesn't say it in the code or in the protocols, it's virtually impossible to meet QII with fiberglass bats in a ceiling that uses roof trusses. Okay, so just be aware of that. Blown-in insulation typically doesn't have this issue. If you absolutely must use bats and you want to use bats, the only way I've seen this work is you actually trim around here to make sure there's no little voids here or gaps, which is a real pain in the butt because there's hundreds of these. Or you put in the fiberglass bats and then you blow a thin layer of like blown-in cellulose, like 2 or 3 inches of blown-in cellulose over the top of it, and that will cover all those little holes and fill in those holes and stuff like that. I would let that slide. Okay. Any kind of loose fill insulation, there's two very important things you have to meet in order to get the R value out of loose fill insulation. The first one is depth. You get your R value. The other one that a lot of people don't know about is density. So depth and density. So depth is handled by your depth sticks, right? You staple those in, make sure the bottom's in contact with the sheetrock, blow the insulation to whatever the R value needs to be. The thing to be aware is these are product specific. So you'll see that this one says, I think that's Knauf, but Jetstream. So this particular brand of insulation has a depth stick for it. So the depth stick needs to match the insulation that's being installed. and they need to be installed one ruler for every 250 square feet, and they have to be readable from the attic access. So they have to be pointed towards the attic access. And then the other thing I mentioned is density. A lot of people don't know about this. And a lot of people, I've had contractors say, I've been blowing in ceiling insulation for 30 years and I've never had anyone tell me this. What the heck is a cookie cutter test? You know, well, that's that tech bulletin I was talking about that was published in 1997. This tech bulletin talks about how to measure density of blown in attic insulation. Okay. And it's basically, you take a sample of a known area and you weigh it, and it has to pass this pounds per square foot requirement that, lo and behold, is labeled right on the insulation bag. A lot of people, they'll see the depth of these other columns that they just kind of ignore. Okay, so you take a sample, you weigh it, and it has to meet the density in order to meet the proper R value. So here's what it looks like on the bag. So this just happens to be Owens Corning Pro Pink. Okay, so you'll see here's your R value. Let's say you want R44. Well, tells you how many bags per 1,000 square feet and all this other stuff, and it'll say installed thickness 14.75. Okay, cool. We'll meet that 14.75. But what they don't see is this one right here, this 0.662 pounds per square foot. That's how you measure that. Well, you take a sample of a known square footage and you weigh it, and it has to be at least, this is a little bit over half a pound per square foot of this insulation in order to meet this R44. Okay, so that is a test that a HERS rater will do, and that is something that installers need to do. If installers follow these requirements on the bags per 1,000 square feet, it should be okay. But what typically happens is they'll blow it in until they hit the depth, and then they stop. They say, oh, let's use this extra on the next house. Well, if you stop too soon, what happens is that the insulation doesn't have the right density and it settles over time. And the depth will actually drop down over time. That's why you have to check for the density. Some interesting situations, like if you have a garage under the same roof as the rest of the house, conditioned space in the attic stops at a certain point. You have to insulate all the way to the exterior surface, exterior wall, and there has to be some kind of a dam up here. A lot of times what happens, you know, back before QII is they just blow the insulation up here and it would just kind of taper off over the attic or over the garage. And then over time, it just settles and settles, and pretty soon you don't have proper insulation on this corner here. All right, so some kind of a little dam here lined up with the exterior surface of the wall. Unvented attics. You're starting to see more and more unvented attics, okay? And that is basically where the attic, the thermal boundary follows the roof line. Instead of following the ceiling, it follows the roof line. Now your attic is considered semi-conditioned space. So the sheetrock between the house and the attic doesn't have to be insulated. They have to insulate it at the roof deck. That poses all kinds of problems, insulating at the roof deck, okay? Don't confuse this with what we call high performance attics. A high performance attic is a vented attic. This is an unvented attic. A high performance attic is a vented attic that has insulation at the roof deck as well as insulation at the ceiling, okay? And that what that is doing is the insulation at the roof deck is acting like a super duper radiant barrier. It's just preventing the radiant heat from coming through the roof and getting into the attic, okay? That's different. This is an unvented attic, okay? And so the point here is that this roof deck insulation has to be the proper R value. The roof deck has to be sealed, as well as the gable ends, okay? This wall in the back here, you can see, that gets treated just like an exterior wall in the house. So that would have to have sheetrock over the top of it because it's a vertical surface, okay? Here is an example. This was actually in Las Vegas. This was Pulte Homes. Another thing that gets missed a lot is the attic access. You have to caulk and seal around the edge, or like a gasket around the edge of an attic access, and the insulation has to be attached to the attic access. If you look really close in this photo, you can see this yellow strapping here. I've seen people will spray adhesive on the back of that piece of sheetrock, put a fiberglass bat on there. As soon as you flip it upside down, the fiberglass bat just peels right off. Okay. This one is actually attached nicely. And then on the attic access itself, on the house where this sits down in there, there needs to be a little, like a little weather stripping edge around there as well. You don't see too many pull down attic ladders. If you do, those have to be insulated as well. There's a lot of different ways to do that as well. Okay. TJI floor joist. TJI is like a wooden I-beam. And so you have to make sure that the insulation kind of pushes out into those gaps created by the indentation on the I-beam. So here's a better diagram. So you see this is a TJI. It's shaped like an I here. And there's a couple ways this can fail. The first way it fails is if the insulation is not in contact with the subfloor. There's a gap here. That would fail. The other way it fails is the insulation is not wide enough. It's not a full width bat, so it doesn't expand out and fill these voids on the sides. That would fail. This is what you want to see, because it looks more like this. Okay, no gaps, no voids, full contact. And that's it. That's the end of my slides. Are there any further questions? Anything we covered? Sorry, that stops kind of abruptly, doesn't it? But that's it.
Yeah,
that's
Russ.
it.
Yeah, we can open it up for questions for a couple minutes here. Otherwise, I'll get that poll launched.
Yep.
Satisfaction survey as we're waiting, and then let people ask their questions if they have any.
Yeah, and again, just go to if you just Google CalCerts QII handbook, a link should pop up. Oh, or you can go to our website, calcerts.com, and in the top bar, there's some tabs. There's one called resources, and you'll see it. Click on resources, you'll see QII handbook. And it has really grown over the years. It is probably, gosh, it's probably like 150 pages now of diagrams and all that stuff. So
it is a fascinating and helpful document. That handbook. It has answered so many questions that I've had to just usually I would just call Russ or send him a text, and I can just get that answered pretty quickly. So it's pretty, just by flipping through it, pretty nice.
Yep. And there's still occasionally people come up with a question that's like a weird situation. We're getting a lot more stuff now on multifamily buildings. Multifamily buildings have a lot of weird things going on, and so we collect those diagrams. If there's a new situation that we haven't covered, we'll create a diagram, and then the next time the handbook comes out, we'll add stuff. So that's why it grows and grows.
Russ, Michael Hicks is asking if we have an example of a full fill vaulted ceiling framing situation.
Yeah. So a lot of times, so there's different kinds of vaulted ceilings. Let me see if I can find a diagram. There's different ways vaulted ceilings can be accomplished. And so here's one. Mostly what I see in new construction and a lot of tract homes is they just make a truss that has a weird, like a scissor truss or something. And so this is all open up above. But another way to do a vaulted ceiling is, instead of a truss, is you use regular dimensional lumber, like a 2x12 or a 2x10. And so this, the roof deck and the inside of the ceiling are on the top and bottom of that framing. And so that's a continuous channel, so to speak. There is a rule that says you have to have a 1-inch clearance below the roof deck. And I've had it explained in a variety of ways. One explanation is, if you get any kind of a pinhole leak in the roof, you want the water to run down the bottom side of the roof deck and get to the bottom so that it can go out the edge. And if the insulation is in contact, that leak soaks into the insulation. Another one is so that air can move through there to prevent condensation and things like that. You can, if you have to kind of get special permission from the building department, but I have seen it where they will allow you to just completely fill that void with insulation. And I think you guys have a lot of coastal zones up there. They don't like to do that on coastal zones because it's more humid,
Right.
and so you have condensation issues. But I know like in Palm Springs and Las Vegas, they don't care. They just blow it full of insulation. You know, they have negative humidity in those places anyways. So you do have to kind of, there's kind of some overlapping codes here. So there's the building code that requires the 1-inch gap, and then you got QII that says you must have the right R value. So the architect and whoever's designing the house needs to coordinate those codes to make sure that that meets both codes. Okay.
Good question. Thanks, Michael. Any others out there? And feel free to unmute yourself. We've got a pretty small group, so I don't think we'll be talking over each other too much.
So Russ, on that question that he was just talking about with the vaulted ceiling with the 2x framing, so are you saying that, like, is QII going to look at that and see that 6 surface hasn't been touched and fail? I mean, theoretically, that's what QII would fail at that point, right?
Actually, because the 6-sided contact is only required on a vertical surface, and so as long as it's like, I think it's 60 degrees is where they determine is the break point. So a vaulted ceiling is at an angle, so it doesn't need 6-sided contact. Okay. The main thing QII is going to want to check for is the R value, because I've seen it where, you know, the plans call for 2x10, and the energy consultant says, oh, I can fit R39 in there. Well, that's if it's completely filled. And then that R39 is conflicting with the code that requires the 1-inch gap. All right. So that's where the coordination has to happen on the design side, because QII requires the right R value, but the building code might require a 1-inch gap. Okay.
Thanks.
Sure.
Hey, Russ, this is Michael Hicks. Can you hear me? Okay.
Yeah.
Yes.
Yep, you can hear you.
Yes.
Michael.
Okay, great. So I guess my question on that 1-inch gap that you're talking about, it's my understanding that if you have that 1-inch gap, then now you need to have ventilation at both ends of that gap running up that 1-inch gap all the way up the roof slope. Is that so? In other words, you have to have either like a continuous ridge vent or holes at the bottom at the eave. Is that a correct understanding, or can you just get a 1-inch gap and not have venting at the top and bottom of that?
Yeah, that's actually not a QII requirement. That's a building code thing, and I've seen it enforced differently in different places. Yeah, technically, well, one building department might say, well, it's not an attic, so it doesn't need the 1 to 130, 1 to 150 attic ventilation. It's not an attic, so it doesn't need that. And then other ones will say, well, what good is having a 1-inch gap there if the air can't go? And so I've just seen it enforced differently. And so I think on that one, the best thing to do is check with the building department on how they're going to enforce that. It's not a QII issue. All QII says is whatever venting is there, don't cover it up with insulation. Make sure it's properly vented. Yeah, that's a tough one. I've seen it. I've seen it. Like I said, I've seen it enforced differently in different jurisdictions.
Mm-hmm. Yeah, just a number of roofers that I've dealt with on the coast have run into situations of where people were in the past doing that full fill insulation in that framing, and the moisture in the wall or in the ceiling space condensing and causing dry rot in the roof framing. So they come to do a re-roof 15, 20 years later, and they're running into a lot of dry rot in the roof framing members because of lack of ventilation. So I think why I was kind of curious.
Yeah, and so the first way to prevent that is to have that air gap, right? That's the first thing. And then the second way is to make sure that the air in that gap can go somewhere and take that moisture away. Otherwise, so to me, following it, the intent of the code would be to say, yes, you must vent each one of those channels on the top and the bottom. That, to me, that would be the most obvious way to prevent that issue. But like I said, some building departments say, well, it's not an attic. So there's nothing in the code that says it has to be vented. We do want the 1-inch gap, but it doesn't have to be vented. And then, when we start talking about unvented attics where they put the insulation up at the roof deck, now building departments saying, but wait a second, that violates the 1-inch gap. So how can you do that? So if you're going to do an unvented attic, you do have to get permission. There's like an exception to the code that they can grant under certain situations. But usually on the coast, they're pretty strict about, because there's so much more moisture, there's much higher humidity on the coast. They're more strict about following the code, and they may not let you do an unvented attic unless you take certain precautions. So yeah, it varies a lot.
Okay. Thank you.
Sure.
Yeah. All right. Any other questions? All right. You sure? I'm going to bore you with my 3C Ren spiel.
Go to yours.
All right. Thanks for all the questions, everyone, and thanks Russ for providing this course for us. I think it's pretty important. We've obviously have given it a few times now in our course calendars, so we're really excited to offer it. So thanks again, Russ. We really appreciate it. And so before we kind of sign off, I just want to provide an overview of all of our great offerings that are coming up with 3C Ren, as well as what our 3 programs are. So I'll just quickly go through that. So Russ, next slide, please. Thanks. So currently we offer 3 programs, the Energy Code Connect, of which this course was brought to you under, our Building Performance Training Program, and Home Energy Savings. Next slide, please. So our Energy Code Connect program serves all building professionals, whether public or private. It works across the public and private sectors and offers services for everyone from plans examiners and inspectors to architects and contractors. So we address residential and non-residential applications of both the Energy Code and Cal Green building standards, and we partner with many professional membership organizations in the delivery and promotion of our program and courses like USGBC, ICC, and AIA. So Energy Code, we offer 3 distinct services underneath the program, one of which is our Energy Code Coach service. It is a free over-the-phone, online, over-the-counter, and in the field service to help building professionals navigate the complex and ever-changing energy code. So this service provides mentoring and support from local experts like Imbalance Consulting and Franklin Energy. So please call our hotline or you fill out a form on our website, which I'll show at the end here, to submit an inquiry. We also have trainings each month, like this one today. And they're free interactive online courses, online for now, hopefully in person again in the near future is what we're hoping. But they're taught always by expert instructors like Russ or folks from Franklin Energy, Imbalance, you name it. And our courses increase overall energy code comprehension, compliance, and enforcement across the territory. And then lastly, we have our regional forums that provide an opportunity to explore aspects of California's energy code that are relevant to critical policy issues facing our region. We just had one last week on heat pump water heaters that was and the heat pump water heater market in our region that I think went really well. And we've had a lot of great feedback. The recording of that, I believe, is on our website at 3c-ren.org. You can seek it out there. We hold those regional forums about 3 to 4 times a year, and hope to see you all take advantage of them at some point. Next slide, please. Similar to the Energy Code Connect program, our building performance training program serves current and prospective building professionals, both public and private. Trainings are offered to architects, contractors, real estate professionals, you name it, as well as plans examiners and building inspectors. Our focus is to expand and to better serve underserved and hard to reach workers. That's really what we're trying to do with this program, as well as deliver trainings that are effective in lifting the tide, so to speak, of building science principles in our territory. We offer expert instruction covering technical skills related to building science principles and systems for high performance buildings. Topics include air sealing, heat pump technologies, zero net energy building principles, and a lot more. We also focus on soft skills such as sales, marketing, and communication techniques to grow businesses, and provide professional education credits, including AIA, ICC, and a lot more. Next slide, please. Sorry. So just to, so if you want to get involved, you can learn more here at these different websites. All these slides, as Russ suggested, will be provided to you in the form of a PDF in an email. So you can utilize these links. They'll be available to you. And next slide. So I don't think there's any ICC units associated with this one, but there are AIA learning units. If you didn't provide your AIA number, please contact Sean Burns at spburns@countyofsb.org to get those units fulfilled and out to you. Like I said, coming in your inbox soon, you're going to have the training slides, the recording of this course, as well as the survey. And then here's just a few upcoming courses that we think you might be interested in the very near future. We have residential retrofits in the 2019 Energy Code on March 25th. We have HRV and ERV for passive house applications on March 30th, integrated design and commissioning on the 13th and the 14th of April. That's split into two 1.5 hour sections because it's a pretty lengthy course, but pretty important. And then we have Russ King coming back for non-res tenant improvements in the 2019 Energy Code on the 20th of April as well. Next slide, please. So that's it. Thank you all. We really appreciate all of your questions and for being here with us. If you have any additional questions, we're here, but otherwise we'll see you at the next one. Thank you.
Thanks, everyone.
All right. Russ, thanks a lot, buddy. It was great.
Thank you. See you at the next one.
Sounds good.